So this is the bending moment problem we set out in class on Monday the 26th of November. So it's a cantilever, 3 metres long with an extra 1 metre bit sticking up, which kind of makes life look as if it's more complicated, but it's not that difficult. Before we get on to the first proper step, which is usually to draw a free body diagram of the whole thing, it's pretty worth thinking about, it's definitely worth thinking about how this thing actually deflects. How do you know how it actually deflects? Well, because you can imagine it. So if you pull to the right, clearly the top is going to want to move to the right, and the whole thing is going to tend to do something like that. Okay, you know that, not through structural mechanics, you know that because you can imagine what happens, and that's potentially helpful. By thinking about the deflected shape, you can think about whereabouts tension and compression will be. So hopefully you can imagine that we will see tension building up on this side of the beam, and similarly, since it's the beam, if I exaggerate it, the horizontal bit is curving something like that, it's the top half which will be in tension, and the bottom half which will be in compression. So we'd be expecting to see the bending moment diagram appear on that top half. So we'll keep that in mind for the second, and draw the free body diagram. So there's the free body diagram, as if by magic. I've shown, well, you need to show where the fixed support is. You need to show potentially 3 forces, a vertical, horizontal, and a moment which the support is applying to the structure to hold it horizontal where it hits the wall. I put in the horizontal force of 3 kilonewtons because it's pretty obvious that's what it is, so I'm resolving horizontally in my head essentially. Also, I'm not putting vertical force because there's no applied vertical force, so there is nothing to balance. The moment I've called F1 for the time being, and it's fairly easy to find F1 using the usual technique. So thinking about moment equilibrium to give us a grip on the moment, and let's say that the sum of the moments, making up this notation as I go along, which is fine as long as it's reasonably clear what it means. So I'm saying some of the moments about the support is 0, so that's this point here. So considering moment equilibrium, what have we got? Well, we've got 3 kilonewtons acting with a lever arm of 1 metre. Okay, so remember that's the line of action of 3 kilonewtons, and it's this distance here, which is 1 metre. So that's acting clockwise. What else have we got? Well, the only other thing that causes a moment is the moment F1, which is applied at the support, and that's an anti-clockwise moment. So we see that F1 is equal to 3 times 1 equals 3 kilonewton meters. Okay. Just in the interest of saving space, I'm going to rub that out in a second and put it straight on the free body diagram. So, okay, so there's a complete free body diagram. How do we find out what the moments are along the beam, so along the 3 metre horizontal bit and the 1 metre vertical bit? Well, making cuts is the technique that we are at first learning how to use, but eventually you should be able to kind of do it in your head and pick up some other characteristics of what we know the bending moment diagram must be like. So it's a process which involves a combination of analysis, but also experience. One thing that we perhaps could have spotted straight away, or could have exploited straight away to even save drawing a free body diagram, is to look at the vertical bit and make a cut which exposes only the applied external force of 3 kilonewtons. So if I then define some x coordinate, so let's say it's x, which starts 0 at the free end, at the tip rather, here, gets bigger and bigger, so this is a positive face here. I'm not going to show shear, because I'm only trying to find moment, so I'm just going to show moment. So what I've just drawn, strictly speaking, isn't a free body diagram because it doesn't include shear, but I'm going to consider moment equilibrium at this free end to find m. So the fact that s isn't there, we're going to live with. So let's say what we're doing as usual, sum about the moments at the free end equals 0. So moment equilibrium, we've got 3 times by x. Oops. Acting clockwise equals m. So m is equal to 3x. What does that mean? Well, when it's x equals 0, which is at the tip of the beam, m is equal to 0, of course, and that's what we'd expect. And m gets steadily bigger, so as we reach the bottom of the vertical bit, it's reached a value of 3 kilonewton meters. How do we plot that? Well, let's draw the structure down here in a sort of large 1, 2, 3 sort of large format. Okay, that's more or less to scale. So the coordinate system I used involves x starting at the tip, getting positive downwards, so x is positive in that direction. With respect to that x-axis, our convention is to show m positive in that direction. Okay, so that our diagrams look the same as everybody else's. So with that in mind, let's show the bending moment diagram in purple. When x is 0, m is 0, so that's 0 here, and it goes up to 3, and goes up to positive 3, and we're showing m positive to the left, as it shows here, so m just gets bigger and bigger and bigger, up to a value of 3. Sometimes people shade this in here, like that. Okay, so to fill in the gaps here, there's a question about what happens in here. Well, one thing that we'll learn from experience is that a moment of 3 at the bottom of the horizontal bit has to transfer straight round into the right hand end of the horizontal bit. So that value there will also be 3. Okay. Now, to find out what goes on where I've shown the question mark, we'll make a cut, but later on, when you become more experienced at this, you should be able to go straight to what the answer is, because as we'll see in a second, it's pretty straightforward. So let's make the cut. It doesn't matter which side we keep or don't keep, because we've worked out the reaction forces already. So let's do it this way. In fact, let's stick to the same colours we used before. So we're going to keep the left hand side bit, so 3 kilonewton meters. Okay, and there's a horizontal force of 3 kilonewtons. This is our positive x direction, so this is our positive m direction. Same as before, I'm not going to show s. We're going to consider moment equilibrium about the free end as usual. So let's say what we're doing. Some of the moments about the free end, 0. So considering that, there's only two forces which cause a moment there, and they're both applied moments because the horizontal 3 kilonewton force goes through that point. Its line of action goes through that point. So we have m is equal to, they're both anti-clockwise, so m must be equal to minus 3 kilonewton meters. Okay, so we're going to plot that on this horizontal line down here. In our head, we're thinking, okay, if x is positive to the right, then we'll show m as positive downwards. So what is m? Well, m isn't even a function of x here, it is just 3. So it starts as 3 up here, and carries along as 3, and finishes up as 3. Okay, and as I hoped, it has the same value as this did down here, so we'll shade that in. Okay, and we also see that the value of 3 here is the same as the support rotational reaction. So that's it, all done.